And you should be able to see on my screen a little GIF image of potassium, sodium, and lithium being thrown into water. And you can see that there is a reaction. Can you see that happening? And then the little bits being labeled afterwards? Okay, so which one of those looks like it's reacted the most with the water? Or which one seems to have the, and I know it's hard to see, they're all swirling around, but by the end, which one seems to be having the biggest reaction with the water? The sodium, the potassium, or the lithium? And you can watch it a couple more times if you need to try to decipher what you're seeing there. I know it's not easy. Yeah, the potassium. The potassium seems to still be burning pretty brightly, and it reacts quite extensively when you put it in water. So then what we're trying to do with this is just kind of see this trend on the periodic table, because we're spending our time now learning about the periodic table, which is this document right here. And all of these elements are group 1 elements. And that means they have similar electron structures, which we'll see in just a minute. And because of that, they all react with water. And you can see that if potassium down here reacts the most, sodium might be the second most reactive, and then lithium is the third most reactive. There seems to be a trend that things get more reactive as you go down this group in the periodic table. So then the question would be, which I had asked there at the beginning, is which do you think would be more reactive, rubidium or cesium? If we're following that trend, which one of those do you think would be more reactive, Rb or Cs? So again, there's a trend. Okay, there's a trend toward greater reactivity as you move down the periodic table. I'm not trying to trick you or anything. There's a trend toward greater reactivity. And we saw that potassium was the greatest of the three we tested. And so now we're going to look at these two and which one of these would be most reactive if we're expecting there to be increased reactivity as we move down. Yeah, right. Cesium. That's all, yeah, that's all I'm trying to figure out. So again, this is the periodic table. These are all the atoms that make up everything in the world around us. Air, gas, liquid, solid, everything is made up by these atoms. And all that differentiates these atoms is simply the number of protons in the nucleus. And then what changes the way they react is the electron. And that's what we're going to look at here. So really quickly, I'll show you that if you actually stick rubidium in water, I luckily have a GIF image of that, you get a very intense reaction inside of this little plastic jar or something like that. And you can see that just dumping here, it is going in a tiny piece, or I guess a little piece, well, a pretty big piece of rubidium in. Instantly, it reacts very violently with the water. And then cesium reacts even more violently with the water, as we'll see right here at this one. It actually, in this case, breaks the jar that it's stuck into, and the water all leaks out. So I guess it stops reacting as soon as the water's all over the floor. So cesium is, in fact, more reactive. And now we can look at the structure of these atoms to understand that. So inside the nucleus, there's protons and neutrons. And we can see here that starting with lithium and then moving up to sodium, it fills up this next shell, but then it has a single electron again in the outer shell, just like this one has a single electron in the outer shell. And these shells get filled up when they have 8. You can see there's 8 electrons inside this particular shell of electrons. I know that a lot of this will sound a little bit foreign to you because we've been studying atoms for a couple weeks, so you're kind of coming in midway through it here a little bit. And then you'll see potassium K is the next one. And again, those electron shells fill up and we have one electron in the outer shell. Can you see how that's working? How there's one electron in each outer shell of these atoms? Okay. And that's, so the rubidium is there now, and then I'm bringing cesium in now, which is the biggest of all. And so what happens is these atoms feel very comfortable when they have 8 electrons in their outer shell. We'll see that again and again. All atoms, any atoms. And these particular electrons, since they're balancing the protons and neutrons, they have 11 protons and therefore 11 electrons, which leaves, in the case of sodium, which leaves this one electron dangling out here on the outside. And they really want to get rid of it, which is why they react so violently with water, because they're getting rid of those electrons. Now, the bigger that they get, the farther those electrons are from the nucleus. So they have even less attraction for the nucleus. So it's even easier to get rid of. And that's why they become more reactive as the atoms get bigger. So that's how that works. Let's go ahead and erase that and move on. I know this might not make the most sense, but I think it'll make some sense as you keep on, as you kind of go back and remember this. Okay, so just so you know, online participation is worth 20% of your grade. So you're going to want to be here each week in class to get that 20%. As long as you're participating and responding, like when I ask questions, and you've been doing that, you're going to get that 20% of your overall grade. So that means you get a reduced homework load. Hooray, right? Oh, this other part doesn't really apply. I guess you must, yeah, you must participate as well, which is kind of what I pointed out. And then if you have to miss a class, you can watch the recording and send me like a 1-paragraph summary of what you watched. But you can only do that twice per trimester. You really need to be here to get credit each time, each Wednesday at 11 a.m. All right, and then the rest of this class, I was kind of talking about an experiment that was done to explore the structure of an atom. Because we've been learning about atoms this whole time. We're kind of going through this part of the class here. And Ernst Rutherford, who is a famous experimenter from New Zealand, found that the original model of the atom didn't seem to be accurate. What he found was the original model looked like this. The idea was all we knew about atoms were there were these negatively charged electrons inside of them somewhere that came out when we did certain things to the atoms. So we just assumed there must be a positively charged mass of something, which we called sort of plum pudding, on the inside. So that's why I have this plum pudding here, to kind of represent that. So it was like the electrons were like the raisins or the plums in the plum pudding, and everything else was a positive mass. Well, Rutherford found something really interesting, which was that when he fired alpha particles at atoms, some of them were deflected. Most of them went right through, like you'd kind of expect if you fired a bullet at a plum pudding. It would just go right through the pudding, right? But Rutherford found that the atoms actually passed, or some of the alpha particles passed right through the atom. So he realized that there must be something going on with the density. And density is how much mass you can fit into a volume. So this is my little density gang sign. Mass divided by volume is density. You'll have to learn that. It's how much mass, how much weight, I guess you could say, you fit into a certain amount of volume or space. So density is a measure of how compact something is. So a plum pudding is kind of spread out, sort of like cotton candy, perhaps. And what Rutherford found was when he fired an alpha particle, like you might fire at cotton candy, well, it bounced back. Instead of going through like you'd expect this BB or whatever to kind of go straight through the cotton candy, he found that some of those particles bounced back. And so he said, there must be something different about the structure of the atom. It must not be like a plum pudding. Perhaps, like if you took cotton candy and squished it up into a tiny, tight ball, it could begin to deflect some of these BBs. And Rutherford, being the boring guy that he was, said that this event was perhaps the most incredible thing that ever happened to him. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. And he had discovered because of this that the atom would look more like this, with a tiny, tiny nucleus where all the mass of the atom was in the center. And even though this shows like these large balls that are electrons, these would not be this big. These would be insignificantly small, so small that there's no point in you couldn't even like have a dot on here. So I'm going to cross them out because it's kind of deceptive how big they look in the picture. Because really they would be so small and insignificant that they would be even less significant than that tiny dot in the middle, which is the nucleus. So that means all the mass of the atom is crunched up in this tiny ball in the middle. So that most of the time, bullets will still pass through, but occasionally they will be deflected because they'll happen to hit or get close to that nucleus in the middle. If you blow up an atom to be the size of a football stadium, that nucleus is literally only a pea in the center of the atom. So most of the atom, the vast, overwhelming majority of the atom, is empty space, with all of the mass crunched into this tiny, tiny nucleus in the center. That's where the protons and the neutrons are. So this plum pudding model, where the mass is spread out, is not accurate. Instead, this is the model. And you can see actually from that model how, in this GIF image, most things would still pass straight through, but as you get close to that nucleus, you'd start to get some deflection of those alpha particles as they got close to that nucleus. Or you can see here, like if you fired a bullet right at the nucleus, if it happened to hit right at the nucleus, it might break. In this case, it wouldn't exactly do that. It would be deflected, but just to give you an idea of how that works. So the most important thing there is that you understand that the mass of an atom is not spread out, but it's all condensed down in this tiny nucleus where the protons and the neutrons make up the majority of that mass. Does that make sense? Okay. Sorry, I know I've been talking a lot, but just a little bit left here. So again, this would be another model of the atom where you'd see 8 protons and 8 neutrons being the mass of the atom, and these electrons around the outside. Now, another question we could then ask is, if everything around us is simply different atoms that have a different number of protons and therefore usually a different number of electrons and neutrons as well, then how is touch possible? How do atoms touch? And this is something you'll have a lesson or two on in week 2. Because if all the atoms in my finger is a really dense center with these little electrons flitting around extremely fast, like at nearly the speed of light, then why does it feel solid? Why, when I put my fingers together, does it seem to be solid? And there seems like this is not electrons on the outside flitting around. This is a solid thing that seems to be touching, right? Well, we'll see that touch actually is a lot more deceptive than that. And in reality, touch may not even actually be possible the way we think of it. Because what's really happening is not that my fingers are touching here, but the electrons, which are negatively charged, flitting around all the atoms in this finger, and the electrons that are negatively charged flitting around on all the atoms on this finger, get close but deflect each other. And it feels like they're touching, but really they're just deforming my skin on both sides and causing electrostatic repulsion to keep them apart. So perhaps nothing really ever touches at all. And so this is some pictures my students have drawn of atoms touching or trying to touch to demonstrate that point. And you'll draw a picture like that as well at some point. Anyway, that's it for class. That's kind of what we went over today. As long as you understand the importance of being in class on Wednesdays and can start going through those modules and get caught up, you'll be fine. This really isn't that hard of a class. I don't ask you to do a lot. I just ask you to kind of stay caught up with stuff. Sure thing, Helen. If you have any other questions, feel free to let me know and give me a call or send me an email or come to my office hours. And you're free to go if you like. All right.